to transfer it so that you organize your this to let it be on one page. Eh?
Yes.
When I reach it,
Mommy, I want to join the class.
when are you joining it?
No.
But I asked you.
Good morning, everyone. I hope I'm audible.
Good morning, sir.
Good morning, sir.
Uh, I can see only about 100 of you online, and I'm very sure that this class is meant to be over 1,000, if not close to 2,000. We are going to have we'll be having class tests henceforth. Whoever is not in class means that the person is not in class. And once the test is conducted, nobody should come back and tell me that that was the day network was bad on the side, because it will not be entertained. So for today's class, I'm going to take carbonyl compounds, not all over again, but trying to be more explicit, because I realized that the last class, though, was conducive. We need to kind of make more explanation for better understanding. So today, we quickly just go over again the slides, but making it more interactive and trying to see how we should, or what we can expect for the examination. Nomenclature is very key when it comes to any examination. So I'm going to share my slides. And because I've done it before, all I'll be doing is bringing up something that I want us to kind of have a better understanding of. So yeah, like I said in the last class, when we talk about carbonyl compounds, those are compounds having the carbon double bond oxygen, and particularly you have the aldehydes and you have the ketone. For these compounds, must say that we are going to be talking particularly about the aldehydes, which is those set of compounds that have the aldehyde, which is having at least one hydrogen, or we have the carbonyl ketone, which is having on both sides at least, carbon compounds. Here is a typical example of the aldehyde. There you can see two carbon atoms, and that is ethanol. Then the second case you have ketone with R on both sides, and there you have propan-2-one. Once you use the board to kind of make some better explanation on that, I have and we are giving this to name in their exam. What do you think will be the name of this compound? Anybody? You make it a random name. What's the name of this compound drawn? Or you can't see my slide or my board rather.
Pentanol.
Pentanol, sir.
No.
Pentanone, sir.
Pentatunal.
Okay. Pentan-2-one, thank you. Because somebody said pentanol, I was going to draw this, and I will expect the same person to tell me what this will be, if this is what we were given today. And I did mention in the last class that when we are having a ketone, it is very, very important for you to indicate the position of the carbonyl carbon. Because once you don't, then it can be any of them. You said pentanone. The first one I label A is pentan-2-one. The second one I label B is pentan-3-one. If you call it pentanone, then which one are you really talking about? Or which one do you think should be the right answer? And I'm sure for your exam, you will have the two of them as options given, and pentanone will also be given as options. So it's very, very important for you to indicate the position of your carbonyl compound, especially when you have a ketone. Similarly, still on that, I have this this one will be what? Yes.
3-methylpentan-2-one.
3-methylpentan-2-one. We have something like this as well. And this will be what? This will be what?
benzene pentanol.
I didn't hear that. I'm struggling to hear what you are saying.
2-benzyl pentatone 2-benzyl
It's wrong.
New ethanol.
You can see it as acetophenone acetophenone or it is phenylethanone. Phenyl.
With not having age for. Hey. No.
Ethanol. Don't mind my writing, my list is there. Phenylethanol. And the logic behind that is that if you look at this one, that's one carbon, this is two. So you have two carbon there.
Okay.
Now, if you have CH3,
My dear. Cool me by favor.
C double bond O,
The
it is
ethanol.
called aceto group.
See.
Aceto. And that's why this is the common name of this compound is acetic acid. So that's where the aceto is from. Aceto from this CH3CO. That's the aceto group. Since what you have left is a phenyl group because the benzene ring has lost its hydrogen, so it's phenyl. And that's why the name was N. See, and that is the ketone that you're having there, the functionality, and the name with what? O. So acetophenylone or phenyl 1,2 ethanol. And that's the two names that this compound can have. Still on that, before I move on to the other parts that I want to stress today, just to kind of give a better understanding, I'm not doing that lecture all over again. You have this. And this we call what? You have two benzene rings attached to a carbonyl carbon, and that will be what? Let me help you. A carbon, a benzene ring with a carbon is called what?
benzyl
Benzyl. Okay, fine. So I've given you an hint, so you can take it from there. So you have and that's the benzyl. So the name of this compound will be what? I don't have much time, and that will be
Benzyl phenol.
benzo. Look at what we did the other time. Benzophenone. Benzophenone. Like I said in the last class, I said you have to try as much as possible to work around a lot on nomenclature. You can't afford to do this course without being very, very good and up to date with your nomenclature. Those rules are very, very basic. You must understand the rules, identify the functional group, you number your carbon chains or your ring so that any substrate available is going to be having the lowest coordinate possible. Then you now name the compound based on the identified functional group, starting from the substituents, the parent carbon chain, and the functional group that you have identified. Once you're able to apply that, I'm sure you'll be fine. That's about the nomenclature. Moving on. Moving on, please to clear this off. So we move on to methods of preparations. I said there are some methods that are peculiar to aldehydes and some are peculiar to your ketones, and some are for both of them. Now, the question is, we have the carbon monoxide and hydrogen at high temperature, eating both of them at high temperature in presence of carbon or as a reducing agent. You can form butanol, you can form ethanol, you can form propanol. And those are the various carbonyl compounds that this particular method is used for. Likewise, we have the air oxidation of butanol. And in this case, just like we know, oxidation of primary alcohol will give an aldehyde, oxidation of secondary alcohol will give a ketone. And in this case, you have ethanol giving you ethanol, you have propan-2-propanol or propan-2-ol giving you propanol or 2-propanol. There you go. You have primary alcohol, you oxidize it to give an aldehyde. And I did caution here that this particular reaction written here, for an aldehyde to be formed, it means that immediately the aldehyde is formed, you are removing it, and that is when you can say you have the aldehyde, because once the aldehyde is formed and you have any oxidizing agent available, aldehyde is very, very susceptible to oxidation. Hence, they will be further oxidized to give you carboxylic acid. But if you have a secondary alcohol, once you have any oxidizing agent, they will be oxidized to the ketone. But if you want just aldehyde to be produced, then you use what is called PCC. That is pyridinium chlorochromate. Is the oxidizing agent, any of its derivatives that you can use to oxidize your primary alcohol to an aldehyde without any further oxidation to the carboxylic acid. And that is why, in this case, citronellol was used. This is an alcohol from rose oil, and when it was subjected to oxidation using pyridium chlorochromate, they had citronellal, which is an aldehyde. And you can see the C double bond OH, the CH2OH is the primary alcohol, has been oxidized to the aldehyde. In this case, we have the secondary alcohol using testosterone, which is a male sex hormone, and using PCC as well, it will oxidize it to the ketone. But any available oxidizing agent can do that, not necessarily, one may not prescribe it ourselves to PCC, since the only product that will be formed is what? Is the ketone. The mechanism of the reaction, I think we have done that one. Just want to kind of give all this information again. Now, for the dry distillation of metal salts of carboxylic acids, where you have calcium acetate and calcium formate, then you will have ethanol. But when you have only the calcium acetate, then you're sure going to have a ketone. And the reason is that a carbon is always lost in the form of carbonate in the course of the distillation. And that is why we are going to have, if you look at this one now, the first one, we have CH3, COO, and COO. So it means that we are having 3 carbon atoms that are bonded, that are involved in reaction with calcium. And at the end of the day, you're going to lose one of them, and you have the 2 carbon chain remaining, which is ethanol. But in the second one, we have only calcium acetate, which is we are using 2 molecules, so meaning that we have 4 carbon atoms involved, and invariably by the time one is lost, we're going to have 3 left. That's why we have the propan 2-one. So we need to understand that.
Yes, sir. But it means if it's true. Even though
Hey, I need to put this video.
ẹ ṣáà máa débí o. Ẹ bá ti bẹ̀rẹ̀ lecture
Can
ẹ
you
máa dé
please mute yourself?
ní wá o. Bóyá next semester la máa bẹ̀rẹ̀ lecture. Exam ni nà. Ẹ tó bá ti bẹ̀rẹ̀ exam.
Who is this disturbing the class?
Bí ọ̀tẹ̀ ọkùnrin sí mi.
One of you is disturbing my class. You are disturbing my class.
Because your auntie is for now. That's all.
So we have this. We can have something in this way. Let's assume we are giving we are giving CH3. Sure. And we have H. Oh no. I want to. Yes, and we have this. What is going to be our product? If you have something like this, what do you think will be our product?
We have aldehyde, sir.
No. Okay, what idea are we going to have?
Butana, sir. Sir, Butana.
Butana, are you sure? We cannot have Butana. How many carbon atoms do we have there, you know?
We have
Octana, sir.
propanol.
That's it. If you look at what we had previously, when we have dry distillation, when we have this, the calcium formate and the calcium acetate, with dry distillation, we have two carbon because one of the carbon will be lost in form of the carbonate, the calcium carbonate. Hence, by the time you have this, what we are going to be having is propanol. So 3 carbon atoms will be formed at the end of the day, while the last one will be lost in form of calcium carbonate. So similarly, we talked about reduction of aldehydes reduction of acid and hydride rather to form an aldehyde. This is peculiar to only the aldehyde. Now the question is, if we use instead of this, we decide to use lithium aluminum hydride. What will be our product? If we use this, what will be the product? If this is used, what will be the product here?
Benzaldehyde.
Ah, We are using lithium aluminum hydride, not the reagent they have used. If you recall, when Professor Asheku was teaching you alcohol, all acid chloride on reduction with lithium aluminum hydride will give you alcohol. So you will have benzyl alcohol or phenyl methanol. The product with this is going to be which is benzyl alcohol or phenyl methanol, and that's your product. But because instead of using this has the power, it has 4 hydrogen atoms, which it can use to reduce. So invariably, 1 mole of lithium aluminum hydride will reduce 4 moles of your substrate. And that is why all the whatever is there will be reduced to an alcohol. But for this reagent that we are having here, this reagent, we are having only 1 hydrogen, and that is why it is mild. We are having lithium aluminum hydride tertiary butoxide. As a result, it has the ability of only replacing the chlorine with hydrogen, and thereby making it to be a mild reducing agent. Another one again is the catalytic hydration of ethyl. That will give you an aldehyde, and if you use the hydrogenation of 2-methyl propanol, you're going to have propanone, especially in the presence of copper catalyst. All these we have done, so I'm not going to put so much on that. Now, on this particular one, so many questions can come around it. Let me just put one new slide here. And that is, for this, we have our aldehyde or ketone, the carbonyl compound, to have reacted with our aldehyde or ketone is said to have reacted with HCl. The general name of the product is called what?
Cyanide.
Do you all agree?
Cyanohydrin.
Cyanohydrin, thank you. Cyanohydrin. If that's cyanohydrin, now I want you to be more specific. Let me do this immediately. I have what will be the name of my product. you can see that I'm carrying out a reaction. I'm not asking you for the structure of the product. I'm asking you for the name of the product. So it means
Ethanol,
that you must understand the reaction. You must know what your product is before you can know the name. Yes.
ethanol cyanhydrin.
Okay. Let's see whether it will be. Here you have Cn. Here you have H. And then you have OH. I have 1, I have 2, I have 3. You can see that that name is not correct. So what's the name of this compound now? The name of this compound is what? Name this compound. You have to name this compound. The bicycle. Yes, that compound cycle. What is the name? The IUPAC name. Just give me the IUPAC name.
Cyanopropanol, sir.
Cyanopropanol. Or 1-cyanopropanol. But like I said, this is one word, and there is no other way it can be. Cyanopropanol is very, very correct. So invariably, what I'm trying to do with this class is that I don't want you to get to the exam and now look at it and now you don't taught us this topic as if it's very simple. Get to exam, without bringing things I never mentioned in class. And the idea is the general name. When you are asked to give the name of the product, you must name it just like you are naming any other organic compound. Going forward, that's it. Hydrolysis of cyanohydride. I think it's there. So yes, hydrolysis of cyanohydride will give you carboxylic acids. So that aspect as well, you should know it. I can't go on that one because I need to move on to alkyl today. Now, also, the carbonyl compounds reacts with Grignard reagents. As a rule, when you have ethanol, you're going to have a primary alcohol. When you have a secondary alcohol, then it means you have any other aldehyde. When you have a tertiary alcohol, then therefore you probably coming from a ketone. Now, I want to add a slide to that side to just give us that quickly. Yes, here now I have this and doing just what we have been doing before. I have this. I was giving this compound. Okay. We are giving this compound. and I was told that it was obtained from a reaction of RMGX. The question is, what is the most likely? Okay, no, let me make it easier. Let me make it easier so that we don't stress ourselves so much. CH3. Okay, I'm told that this particular alcohol was obtained by the reaction of methyl magnesium halide with a carbonyl, and you are asked, what is the carbonyl that was used? What will be your answer? What is the name of the carbonyl that was used?
Aldehyde, sir.
You said?
Aldehyde.
Yes, an aldehyde. What is the name? But you don't know what carbonyl. It's just they want to give the name of the carbonyl that was used.
That's
Probably
hexanol.
pentanol, sir.
You said? I didn't hear that.
Maybe
That's hexanol,
pentanol,
sir.
sir.
Okay,
No.
let's number the carbon atoms. We have 1, here is 2, here is 3, here is 4, and this is 5, and here you have the 6th. So if 1, because we have methyl magnesium halide, 1 is from the Grignard reagent, then every other thing is the carbonyl compound, and therefore I have 1, 2, 3, 4, 5. The carbonyl compound, therefore, is going to be 1, 2, 3, 4, 5. And here I have hydrogen. And the answer is pentanol. Pentanol. I hope you are all following.
Yes, sir.
For those that are maybe if I advance, you have even exceeded 300. I can see only okay, we just hit 300 now. For any other person joining, it's being streamed on YouTube, so you can always check it there. Just you can join via YouTube, and then you'll be able to see the class that we are holding at this time. So don't give the excuse that the class is failed as well, not a class. And like I said, when the test is given, don't come back and cry foul to me that this is what has happened to you on the day of the test, because no excuse will be taken from anybody. So moving on.
Sir, when are we having tests?
It will be announced. You know, you have class work is there, then we have our test at the appropriate time. Don't worry. But the test will be announced. But for now, we are having class work. So it's the class work I'm talking about. Nobody's going to beg me for anything after announcing that. If you are not there in the class, don't come to me and say this is what is happening. Okay.
So how will we get the YouTube link?
Okay, I didn't put YouTube link on the. Okay, let me quickly put that on your page.
And sir, please, what topic is this? New compounds. Oh. And please, what topic is this?
Just a
It's on the
moment.
slide now, carbon.
Okay. So that's YouTube link. So you can always join there and see what we are doing. It's still the same thing that we are doing here that is going on there. So moving on, we come on to the reactions with derivatives of ammonia. Like I said the other day, we have hydroxylamine. The product is, the general name of the product is an oxime. The hydrazine will give you hydrazone. Phenylhydrazine will give you phenylhydrazone. And of particular interest is the Brady's reagent. Brady's reagent is one of those reagents that we use to check or to confirm presence of carbonyl compound. The moment you add Brady's reagent to your unknown compound and you are able to have a yellow crystal formed, then that compound you are given is most likely a carbonyl compound. Could be an aldehyde and could as well be a ketone. You can always check out which is this at the end of the day. Now, that's the mechanism. Nucleophilic addition of the lone pair of electron on the carbonyl carbon, then transfer of chain electron from the carbon onto the oxygen, and invariably there is loss of water. That's the emission of water, and therefore you have the semicarbazole, which in this case is from reaction with semicarbazide. Now, we also have reaction with phosphorus pentachloride. When you have reaction with phosphorus pentachloride, the carbonyl will be completely lost and two chlorine atoms will be added onto it. So you can convert your carbonyl compound, in this case butanol, to 2,2-dichloro pentane. So you can be asked, what reagents will react with your carbonyl compound and you have a dichloroalkane or dialloalkane? Then you should know that that is what? Potassium pentachloride. Then, moving on quickly, we have just few more minutes. I want to make sure I spend just 1 hour on this before I move on. Alkyl halide, like I've been saying. The alpha hydrogen, that is the carbon next to the carbonyl compound of your carbon next to carbonyl compound is acidic. By that, I want a new slide here. Let me produce a new slide here. I have my one again. Let's assume I have CH3. I'm using ethanol. I'll go back to that slide very shortly, but I want to explain something here very well. That's why I'm using the board. This ethanol, for example. Now, this carbon here, this is the functional group. The carbon next to it is called alpha carbon. The hydrogen on that carbon is called alpha hydrogen. So this H3 is the alpha hydrogen. is said to be acidic, i.e., it can be lost. And by that, in the presence of a base, OH minus, you can have it becoming minus H plus. It becomes CH2 negative, and then everything remains. And that's your H. You may now wonder, why is this compound, why is this possible? Because this compound or this intermediate form can be resonance stabilized. I'm sure with your class, with either Mrs. Anita or Dr. Abayomi, they must have mentioned it, and this is Dr. Abayomi. When this one, okay, probably Dr. Mrs. Anita, when this one comes down, this will go up, giving you another canonical form. So you have CH2 double bond CO minus, and you have the hydrogen. Now, the fact that this intermediate can be stabilized means that this proton can be lost easily. And once that proton is lost, this particular intermediate formed can now react with another ethanol to form a new compound. So if that is happening, you're going to have another ethanol, CH3, C double bond O, and you have the H. This, rather than going this to form the new product here, it will be reacting. It will rather react with this. It will attack this, and therefore you form this new product, CH3, this become O minus, and that becomes the H. And you have the CH2, and you have the C double bond O, and you have the H. Now, the lost hydrogen will now come back to the hydroxyl group to give an alcohol. This product formed I will write it again. This product formed is called aldol condensation. You can see that two molecules of ethanol has combined together to form the aldol condensation. You can have it with an aldehyde, you can have it with a ketone. Both of them are undergoing the same kind of reaction. And depending on whether it is an aldehyde or it is a ketone, the reaction will still follow the same pattern. And now we also need to understand that this particular adult product can as well undergo dehydration minus water in presence of sodium hydrogen sulfate, sodium hydrogen sulfate. It will lose a molecule of water and that molecule of water is going to be, let me remove this, rewrite it. I want to rewrite that. I'm not removing it just like that. So I can remove the molecule of water. So you have the H up here. So this will come down and this will be lost. So invariably, I have CH3. Okay, don't worry, let me do it this way. CH3. Then I still have an H here. I have a C double bond. Okay, there is still another carbon. That is CH, and I have a CHO. So invariably, this is my alpha carbon. I have a beta carbon here, and this is gamma. So you are going to form an alpha beta unsaturated carbonyl compound at the end of it. Because the hydroxyl group is gone, and therefore you have that. So this and many other it is. Now you could be asked, what is the name of this compound? This is 1, 2, 3, 4. So you have 2-butynyl. So these and many others are the things that I want you to kind of put into perspectives when it comes to this aspect of the course, because the question is going to come in so many forms, and you come back and say that it was never mentioned in class. I wonder where they get this kind of question from. And finally, before I close the aspect, you can still see many of them there that we have used. You have the cleansing condensation, which is cross-hadron condensation, in which case one is having alpha hydrogen, the other one is not having alpha hydrogen. And lastly, we have the Cannizzaro. The Cannizzaro reaction is talking about those aldehydes that are not having those aldehydes that don't have alpha hydrogen. They undergo self-oxidation and self-reduction in the presence of a strong base and strong alkali rather. And invariably, when you use that, one acid salt is formed, the other one is going to be an alcohol. But in a situation where we have cross Cannizzaro reaction, the smaller butanol is preferentially attacked by the hydroxy group, which is oxidized to an alcohol, to the carboxylic acid, while the aldehyde is reduced to an alcohol. That's reduction. Then we also have the alpha reaction. The alpha reaction is that reaction of that carbonyl compound in which you can have the acetyl group. You can see here, you have this fraction. You can make this fraction out of your compound. As long as you can make this CH3 double O out of your compound, then such carbonyl compound will give positive iodoform reaction, and we usually see it as a yellow crystal with distinctive smell at the end of your reaction. The last bit there is the reaction that is used to differentiate your aldehyde and your ketone, which is oxidation. You have the phenys, as you have the phenys. You have the phenys solution, and so you have the phenys solution and you have the toluene solution, and that's what you use to differentiate between them. And that's the end of that aspect. So I'm going to share this other slide now. Let me stop sharing this, or let me just come back to share and change it to the alkyl halides. So let me share this. Yes, this is what we are meant to be discussing today. Alkyl halides. Alkyl halides are organic molecules containing halogen atom bonded to an sp3 hybridized carbon. You can see here, I have a carbon. Around that carbon, you have 4 different bonds, single bonds around the carbon, and that is why it is an alkyl halide. Once that carbon is not sp3 hybridized, then it cannot be an alkyl halide. As you will see when we get to discuss the different types of alkyl halides, or different types of halides rather. Now we have different classes of the alkyl halides, which can be primary, secondary, or tertiary, depending on the number of carbon atoms bonded to the carbon with the halogen atom. If you have 3 halogen atoms bonded to the carbon bearing the halogen, then you have methyl halide. There you go. There it is. We have the carbon bonded to the halogen. We have 1, 2, 3 hydrogen around it. So that will be methyl halide. When you have only 2 hydrogen atoms bonded to the carbon, to which you have your halogen, then you talk of secondary alkyl halide. When you have only primary alkyl halide, when you have only 1 hydrogen atom bonded to the carbon bearing the halogen, talk of secondary alkyl halide. And when there is no hydrogen at all to that carbon bonded to the halogen, then you talk of tertiary alkyl halide. You can as well come this way, that when your carbon bearing the halogen is bonded to only one carbon atom or alkyl group, you have a primary. When it's bonded to two carbon atoms or two alkyl groups, it is secondary. And when it is bonded to three carbons or three alkyl groups, then it is tertiary. We also have other types of organic halides. We have the vinyl halides, we have the aryl halides, we have the allylic halides, and we have the benzylic halides. I think at this point, I want to bring back my annotation and insert another slide again. Let me insert a slide there. This slide. Oh, good. You have the vinyl halides when your halogen atom is bonded to a carbon-carbon double bond. We are having something like this. And because the chlorine is bonded to a carbon-carbon double bond, this is a vinyl halide. Vinyl halide. We have the phenyl halide. Phenyl halide when the halogen is bonded directly to a benzene ring. Your chlorobenzene is phenyl halide. You have the phenyl halide. Then you also have the benzyl halide. Benzyl, we have mentioned the other time, when your benzene ring is having a carbon attached to it. That's benzyl. That's your benzene ring. You have a carbon to it, and to that carbon, you have an halogen. Then you have benzyl chloride. That's your benzyl chloride. Or benzyl, as we call it. Benzyl chloride. And the last one is when you have a double bond. And then you have an sp3 carbon in between it, or a CH2 between it and the chlorine, sp3. hybridized carbon. Then this is called allyl. Allyl halogen. Now, if you come here, vinyl halides, halogen atom bonded to carbon double bond. Aryl, the halogen atom bonded to a benzene ring. That's your aryl. Allylic, the halide bonded to the carbon atom adjacent to carbon double bond. This is double bond. Carbon next to it is the adjacent carbon, and that's where your halogen is. And the last one is benzylic, where the carbon atom adjacent to benzene ring is what is the halogen is bonded to. This is the benzene ring. Carbon next to it is CH2 and is bonded to an halogen. That's your benzyl halide. So those are the 4 types, and you must be able to identify them. They can come in any form. You should be able to know which one is which and how you differentiate them. So that's the different types of aryl. So moving on, nomenclature. We have trying to show the various types that we have talked about, either as well as the aryl and sp2 hybridized, the allyl as well as the alkyl halides. They are sp3 hybridized. That is the carbon to which the aryl, the allyl alcohol is bonded. The sp3 is allyl as allyl as well as benzyl. Well, today we have to give the hyperactive of the compound. We release the carbon shade as appearing. At the end of the day, we have 2-chloro-5-methyl heptane. If you don't get that, then that means your numbering of the longest carbon shade is probably wrong. If not, that should be your answer. Now, generally, common names are often used for simple alkyl halides. You name out the carbon atom of the molecule as a single alkyl group and name the halogen bonded to the alkyl group. Combine the name of alkyl group and halide, separating the ones with a space. We have so we have that third butyl, because the carbon there is a tertiary butyl, it's a tertiary carbon, and since you have 4 carbon atoms, that's butyl, and then you have iodine, because that's from iodine. We also have ethyl, and that's why that one is called ethyl chloride. They are weak polar compounds and they exhibit dipo-dipo interaction. So the dipo-dipo movement is there, and that gives it to, I mean, that's what's responsible for majority of the reactions, is relatively reactive compared to other alkanes. Physical properties. We also have these are the interesting alkyl. You have the methyl chloride or chloromethane. It is often found in volcano emissions. We have dichloromethane or methyl chloride, which is often a very important organic solvent. We are also having annotate. That's a safe anesthetic that is used during operations. There are some other ones, Teflons, the polyvinyl chloride, pipes and insulations, DDT, that's the pesticides. Then you also have so you have the freon as well. All these sets of organic compounds, to a large extent at this time, they have been restricted because they have effects on the ozone layer, which is part of what is responsible for the various climatic changes that we are experiencing, especially around this time now. So you could see the electrostatic potential map of the four simple alkyl halides. Now we have that. And you could see the relative map for the simple alkyl halides, and you will observe that the carbon is electron deficient, and that is why most of the reactions of the alkyl halides involves but the carbon is not deficient, is looking for a nucleophile to react with, and that's why your alkyl halide is always undergoing nucleophilic reactions. So the carbon is polar, so a nucleophile, that's electron the nucleophile will react with the alkyl halide, displacing the halogen to form the product. And the alkyl halide will as well addition reaction with roasted down bases and use HX to form an alkene. For nucleophilic substitution reactions, three components are necessary. You have the alkene group, the nucleophile, and the last one is the leaving group. Alkene group of the alkyl halide, is it a primary? Is it a secondary? Is it a tertiary? There you can see for the methyl chloride, the alkyl group there is going to be the methyl. The nucleophile is the hydroxide ion, and the leaving group is the chloride ion, because methanol was formed at the end of the day. One could see clearly that single charge nucleophiles, the likes of hydroxide, the thiol, are usually used, and they are counterbalanced using the alkali metals, and invariably we form an alcohol, a thiol. But when you have a neutral nucleophile, then the product is going to be bearing a positive charge. So when you have this, look at this one now. We have the propyl bromide reacting with dimethylamine, which is a neutral nucleophile. At the end of the day, an ammonium ion was formed. We can see when the nucleophile is having oxygen or a nitrogen, what we have is a positively charged ion which will undergo proton transfer to give a final product which is neutral. Now, in order to draw the product of your substitution reaction, we must identify the sp3 hybridized carbon with the leaving group. We identify nucleophile, that is the species, with the lone pair. Then we now substitute the nucleophile for the leaving group and assign charges if necessary. And that's to be able to get the atoms and the bonds that are formed or broken. The leaving group is usually the usually the halide or the halogen that is attached to the alkyl group. And you could see here, the example given is water is a better living than the hydroxide because water is a weaker base. As the basicity is increasing, then increasing living group ability. That's going from nitrogen to oxygen across the period. But now the group within the algae family, basicity is increasing. Basicity is increasing as you come up the group that is has come from bromine up to chlorine up to fluorine. Or you can say that basicity decreases down the group, whereas the living group ability is increasing down the group. Trying to give the pK value, we have to understand how they are. That's another one. Four living groups. So you have that. The profile. That's the compound with the low pair of electrons or a pi bond but it's always attacking central carbon atom. Nucleophiles attack the electrons of the carbon atom, whereas your base will attack the protons. So what you're trying to tell you there or differentiate there is that both the nucleophile and the bases have no pair of electrons. But for the base, it's targeting a proton because there's a proton and constant, whereas the nucleophile don't share those electrons. So these don't need electrons. So nucleophilicity and basicity are related, but one thing you have to understand is that there is room for them to be par, and at times they are not in the same par. And that's why we must understand the nucleophilicity as well as basicity. How basicity has to do with how readily a particular base attack or releases electron pair to the proton, whereas nucleophilicity is the measure of how readily it attacks a carbon deficient center, and they are not completely the same. Nucleophilicity finds 23 instances for two nucleophiles with the same nucleophilic atom, stronger base, stronger. A daily charged nucleophile is always a strong nucleophile that is considered acid. Right to left across the row of periodic table, nucleophilicity increases. So one can always be sure that for the fluoride, the hydroxide, the amine, and the carbanion, as you go from fluoride down, you are increasing basicity and you are increasing nucleophilicity. Nucleophilicity does not parallel basicity when steric hydride becomes important. So because of that bulkiness, nucleophilicity and basicity cannot go together. So you have that ethoxide is a stronger nucleophile, but butoxide is a stronger base. A base will attract a proton, a nucleophile is ready to donate to the positive center. So while the nucleophile is a stronger nucleophile, that will kill a stronger base. That is submitted sodium. Nucleophile in polar protein solvents. Nucleophilicity increases down the column of 20 as the size of the atom is. This is the opposite of this. You can see that as we come from fluorine down the group, we have increasing nucleophilicity. So we have that for the nucleophiles in polar protein solvent, the likes of water and methanol. Polar means it is charged, protein it has a proton, and that's why you see on this one as an example. Then when you have polar a protein solvent, the likes of acetone, acetonitrile, tetrahydrofuran, and the rest of them, they do not interact by OH or NH, as they are incapable of so all these are nucleophiles that can be used, but in a protein where there is no proton in the solvent. These are the nucleophiles, and now they are being submitted for the reactions to be able to carry go on. So basically decreases as the size increases. Now the column ditto for so we have that the basicity decreases as the size increases. Now the column and nucleophilicity decreases as well. Those are the various nucleophiles used in organic chemistry. Now, the mechanism of the reaction. We have the sigma bond between the halogen and the alkyl is the alkyl halide broken. The nucleophile when that bond is broken, a new bond is formed with the nucleophile, and therefore the halogen will be the leaving group. There are three possibilities of the ways in which the other bond breaking and bond making. The first one, bond making and bond breaking occur at the same time. So that one is called a concerted mechanism. As bond is formed, another one is broken. And in this case, the mechanism is just one step. It's bimolecular, rate dependent on the collision of both reactants and the reaction is usually dependent on the collision of both reactants, that is the nucleophile as well as the alkyl halide, and the rate equation is second order. So you have your rate is equal to K into Rx to the nucleophile. The second one, or second type of or second possibility is that bond breaking occurs before bond making. In this case, the halogen or the leaving group is broken off from the carbon in the alkyl halide, followed by resulting into a carbocation intermediate, which is now attacked to form the product. The first step is rate determining and depends on the constitution of the Rx only. So the first step is rate determining, as a result, the rate depends on the constitution of the Rx only, that's the alkyl halide, and the rate equation is first order. The third possibility, which involves the nucleophile attacking, that is bond making before bond breaking. The nucleophile will attack before you have the halogen leaving. For this one, mechanism has an inherent problem. The intermediate formed or generated in the first step is having 10 electrons around the carbon, which is violating the octet rule. And as a result, this particular possibility is not regarded, is abandoned. Here is typical reaction. We have methyl bromide reacting with acetate. Methyl bromide is sp3 hybridized carbon. For this particular reaction, both reactants appear in the rate equation. Suggesting that we have a bimolecular reaction with one-step mechanism. This is called SN2, substitution nucleophilic bimolecular mechanism. And the rate equation, the rate expression is rate equals to K into the nucleophile as well as the alkyl halide. There is another one here. We have tertiary methyl bromide react with acetate and the product was formed. So you have that, and the kinetic data shows that rate reaction depends on the condition of only the acute energy, because this time around they are having essentially acute energy, and can be stabilized by hyperconjugation, and therefore involves is the only one that is involved in the rate determining step. This is an example of nucleophilic submission nucleophilic unimolecular mechanism. For the SN2, as the acetate is attacking the methyl, the bromine is giving the, and that's why that is having that. That's the transition state diagram, where you have the two of them, you have a higher energy, and by the time the bromine is lost, then you have a lower energy than what you have for the acetate. Methyl bromide. One thing to note, the stereochemistry of your product. When we have SN2 reaction, it's always proceeding via a backside attack of the nucleophile, and that many a time inversion of configuration at the stereogenic center. Since the bromine is already on one side, the nucleophile will have to come from the other side, and that's what leads to inversion of the configuration in the product. You can see the various forms that they are using. They use a tire, they use an hydroxide, and at the end of the day, you have the inversion of configuration. So generally, as number of R group on the carbon giving group increases, the rate of SN2 reaction decreases. So we rather not go through SN2, but the secondly, we react slowly, and tertiary we never undergo SN2. That's showing the inversion of configuration, how they are, and how they affect the steering group effect, how it affects how the
I can't hear you well, sir.
I said here you are just giving an idea of the effects of the bulky groups around the alkyl halide. You can see that for the methyl, the nucleophilic reaction can attack easily, but for the ethyl, something is there to disturb it slightly. By the time you get to secondary when you get to isopropyl, you can see that the nucleophile is almost like struggling. By the time you get the tertiary, it won't have any access at all because of the bulky group around it. And that's what they are trying to show here. So I'm going to leave us at this point. God willing, next Monday, we round up our class on nucleophilic, alkyl halides, and I'm going to probably just take tutorial questions on next week Thursday, and that's where I'm going to round up my own class. So if you have questions, let me entertain one or two. If there is none, then I will wish you all the best as you enjoy the rest of your day.
Good morning, sir.
But
Please, are we going to get the slides for the previous class we had on carbonyl compounds and to this class too as well?
we tried. I'll try and find a way of putting this on the YouTube so I can have access to it. Okay, if there is no other question, enjoy the rest of your day.
Thank you, sir.
Thank you so much, sir. Bye-bye,
Does
sir.
anyone have the complete slide?
Thank you, sir.
Thank you, sir. We appreciate, sir.
Hello, please. Does anyone have the complete slide? I'm not